Good morning students, welcome to the next lecture of electronic measurements and instrumentation. My name is TSS Nagapavan Kumar. Today we will see the concept of digital Fourier analyzer under the wave analyzers topic. Okay, so the second unit wave analyzers, we have the last one, digital Fourier analyzer. So the name itself, it is explaining the complete operation, digital Fourier analyzer. So in this analyzer, we are going to see we are handling the data of digital data, not the analog data, and here we are using some of the Fourier analysis for this data. So finally, we will show the digitalized output data. Let us see. This is the basic view or the basic principle behind the digital Fourier analyzer. The basic principle behind the digital Fourier analyzer is representing with this picture. So here we have an analog continuous waveform. So this is the waveform which is sampled for time t. That is, we have some time period t, and we have some n number of samples. So see here we have n number of samples and we have some time period of t, right? So these are the waveforms here we have. This is a portion of n number of samples here we have. Right, here we have n number of waveforms sampled for time t, and here we have n number of samples. These information, these type of signals, we are giving to the fast Fourier transform processing unit. So this is a processor which is with FFT, fast Fourier transform, FFT processor. This is an FFT processor. From this FFT processor, we are giving to the CRT display of the spectrum analyzer, where this CRT display is equivalent to a parallel filter bank analyzer having n filters with bandwidth of 1 by t. So see here, so we have two types of spectrum analyzers. One is parallel bank filter based spectrum analyzer. Second one is a spectral technique based spectrum analyzer. So this is the parallel filter bank based spectrum analyzer. We have large series of filters, nearly 32 or 40 or 50. The series of filter banks here we have. That type of principle based CRT display, spectrum analyzer CRT display here we have. So this is the explanation regarding about this block diagram. Let us see the theoretical description about this digital Fourier analyzer. Remember, here we are giving a input signal with with a sampled signal with a time t and n number of samples. So the digital Fourier analyzer converts the analog waveform over time period t into n samples. The discrete spectral responses Sx of k.Δf, Sx of k.Δf. Okay, so this is a spectral response of the discrete information, where k is equal to 1 to small so on capital A, where n is the n number of samples, which is equivalent to the simultaneously obtaining the output from n filters. We have n number of filters in that spectrum analyzer technique. So here we have n number of filters having a bandwidth given by delta f is equal to 1 by t, where delta f is equal to 1 by t, where t is the time period of the particular input signal of the samples, is obtained by applying a discrete Fourier transform, where we are applying to a DFT, discrete Fourier transform, to the sampled version of the signal. The spectrum analyzer response is thus given by Sx x of n into del t function. Here we will see Sx of k.Δf is a complex quantity which is obtained by operation of all samples of x of n into del t. So before that, Sx of k into del f we have to see. So first of all, here we have written Sx of k del f is equal to Sx of k del f is equal to, that is equal to T by capital N. T by capital N is a sigma of small n is equal to 1 and to up to capital N, where summation small n is equal to 1 to capital N into del t exponential of minus j 2 pi kn by capital N. Here we have to see Sx of k del f, where the spectral response of the signal is equal to T by N into sigma small n is equal to 1 to capital N x of n into del t exponential of minus j 2 pi kn by n. So this is the given function where Sx of k del n, where Sx of k into del f. Okay, so this is the given function Sx of k del f. Right. Sx of k del f is a complex quantity which is obtained by the operation of all samples of x into n into del t, where x into n del t is equal to all samples are obtained from the given input signal, where small n is equal to 1, 2, 3 so on capital N, right, where small n is equal to 1, 2, 3 so on capital N by the complex factor of exponential minus j of 2 pi kn by n, j of minus j 2 pi kn by n. This is a complex factor parameter. The discrete inverse transform is given by, so that is for Sx of k del f, for that function we have to take the inverse Fourier transform. Inverse Fourier transform we will see later. First we will see the inverse transform of the function. So from the Sx of k del f function, we are taking x into n del t is equal to, so previously that we have written t by n, here we have written t by n, here now we have to write n by t into sigma small n is equal to 1 to capital N, Sx of k into del f exponential of minus j 2 pi kn by capital N, where small n is equal to 1 to so capital N. Since Sx of k del f where k is equal to 1 to so n is a complex quantity, that the DFT provides both amplitude and phase information at a particular point of the spectrum. For the Sx of, where this Sx of k del f function, we are providing amplitude and phase informations. For this spectrum, we are providing amplitude and phase information, where amplitude information is n by t and phase information is equal to exponential of e power minus j 2 pi kn by n. Okay, the discrete transforms are usually implemented by means of the fast Fourier transforms. Most of the discrete functions we are implementing by using FFT technique, fast Fourier transform, which is particularly suitable for implementation in digital computers, since n is constrained to the power of 2, that is equal to 2 power 10 is equal to 1024, like that, where n is the constraint of the digital technique. So most of the computer based processing systems or algorithms are completely dealing this digital Fourier analysis. For this digital Fourier analysis, we have to follow this basic functionality. This is a basic spectrum definition. Let us see the complete block diagram. Let us see the complete block diagram of digital Fourier analyzer. So this is the basic block diagram or the block diagram of the digital Fourier analyzer. This is a complete block diagram of the digital Fourier analyzer. In this digital Fourier analyzer, we have channel 1 and channel 2. Two types of inputs we are giving here. The total block diagram is divided into 3 sections. let us see. The block diagram of digital Fourier analyzer is consisting of three parts. The first one, input section. This is the first one, input section. Second one, control section. This is the second one, control section. Third one, display section. Right? First one, input section, control section, next display section. Totally three parts are available in this block diagram. First part, second part, third part. Total three parts are there in this digital Fourier analyzer. First part is input section, second part control section, third part display section. And here we have two inputs, channel 1 and channel 2 informations. And next here we have a noise generator separate circuit and internal input external trigger circuit. Right? So these are also we will see. So first one, channel input 1 and channel input 2 and input external trigger circuit, noise generator circuit. So these are the very important and key points for this block diagram. So in this block diagram, first we will see what are the inputs, channel 1, channel 2 inputs and input external circuit and noise generator circuit. Next here we have input section, control section, display section. The display section is consisting of a character generator and a CRT section, So this is the display section knob consisting. Right? Okay. So from this you can take directly the printouts, otherwise you can connect to the external CRT for getting more clarity information. So this is the display section. Next, control section. A control section which consisting of FFT processor and it has some memory for nearly 48 kilobits of information, and here we have a keyboard controller. That means a keyboard or controller, FFT processor and 48K memory is available in the control section. Now coming to the input section. In this input section we have two parts. The first part is channel 1 information. This is the channel 1 section. This is the channel 1 section. This is the channel 1 section. This is the first one, channel 1 section. Next, this is the channel 2 section. This is the channel 2 section. Right. So this is the channel 1 and channel 2 sections. Right. Channel 1 and channel 2 section. In the channel 1 section, we have 30 kilohertz, 300 hertz, two types of blocks are available, and here we have here also 300 hertz, 300 hertz and 30 kilohertz, two blocks available, and here we have the output of the signal. Here we are getting is 12-bit ADC output, 12-bit ADC output. Here we have 12-bit output. Here we have 12-bit output. One is sine information, another one is cosine information. These two signals we are adding here. These two signals we are adding to here. These two signals we are adding to here. One is sinusoidal signal, another is cosine sinusoidal signal. These two signals are we are connecting, and these two signals are output of the first section. One way it is going to the control section, and another way it is going to the display section. The controlled information will be again connected to the display section here. So this is the complete block diagram of the digital Fourier analyzer. This is the basic explanation view of the block diagram of the digital Fourier analyzer. Okay, right. So this is about Fourier analyzer. Once again, see clearly the block diagram of this one. Next, the digital signal Fourier analyzer employs an FET algorithm, right? So, the digital Fourier analyzer has a FET algorithm based processor. The block diagram is divided into three sections, namely input section, control section and display section. The input section again consisting of two identical channels. It has two identical channels, channel 1 and channel 2. The input signal is applied to the input amplifier where it is conditioned and passed through two or more anti-aliasing filters. So first we have in these channels, for channel 1 and channel 2 we have an amplifier section which is to be conditioned. Then we have two anti-aliasing filters. So while passing through this anti-aliasing filters through the 30 kHz and 300 Hz, the cutoff frequencies of these filters are selected with respect to the sampling frequency being used. The cutoff frequencies of these filters are selected with respect to the sampling frequency being used. Whatever the sampling frequency you are using, based on that frequency, you are using the cutoff frequency for that filters. You are using the cutoff frequency for that filters. The 30 kHz filter is used with a sampling rate of 102.4 kHz and 300 kHz filter with a sampling range of 1.024 MHz. Here we are using one is 102.4 kHz, the first one. Second one is nearly 1.024 MHz frequency range for 30 kHz and 300 kHz. Two types of frequency bands are available. One is the 30 kHz, second one is 300 kHz. Both has different types of sampling rate. Next, to convert the signal into digital form, a 12-bit ADC used. If you want to process this data, this analog signal you have to convert into digital form. For that I am using a 12-bit analog to digital converter. A 12-bit analog to digital converter, that is a 12-bit ADC I am using. The output from this ADC is connected to a multiplier and a digital filter. The output of this ADC I am connecting to a multiplier circuit and a digital filter circuit. Depending on the mode of the analyzer to be used, either baseband mode or in the band selectable mode. So baseband mode means in which the spectrum is displayed from a DC to an upper frequency within the bandwidth of the analyzer. This is a baseband mode. Or in the band selected mode, the band selectable mode, that is which is it allows full resolution of the analyzer to be focused in the narrow frequency band. These are the two types of modes are available. The signal is multiplied either sine or cosine function. These two signals are multiplied by with a sine or cosine functions, sine and cosine functions. The processing section of the analyzer provides FET processing on the input signal, linear and or logarithmic algorithm. So here we have a FET processor based section for that given input signal. For one channel, this can provide the real magnitude. For one channel, we are providing the real magnitude information and other imaginary information for the linear spectrum of Sx of t. So one is directly we are giving Sx of t to signal. Another one we are giving for Sx of t complicated signal, that is a complex signal of Sx of f. One is Sx of f original information, another one is Sx of f star, where star indicates that's complex function of the signal, where Sx of f is equal to Fourier f of x of t. Some function of x of t is equal to Sx of f, where f of x of t is the Fourier transform of x of t, where this capital F is representing Fourier transform technique. F of x of t is equal to Fourier transform of x of t. It's not some function of x of t. The auto spectrum gxx of f, auto spectrum for the same input function. We have input function x of t. Auto correlation, how we will define gxx of f? Gxx of f, which contains no phase information is obtained from the Sx of t. Autocorrelation function does not have any phase information. That information we are representing Gxx of f, where Gxx of f is equal to Sx of f into Sx of f star. That is the original signal and the complex conjugated signal. Both signals multiplied information you will get for autocorrelation function of Gxx of f, where Sx of f star indicates the complex conjugate of Sx of f. This complex conjugate of Sx of f is equal to Sx of f star. The power spectral density PSD is obtained by normalizing the function Gxx of f to a bandwidth of 1 Hz, which represents the power in a bandwidth of 1 Hz centered around the frequency of f. So the PSD based signal is normalizing with the function of autocorrelation function, that is Gxx of f. Next, the inverse Fourier transform of that function Gxx of f is we are representing with Rxx of tau. Rxx of tau we are representing here. So this Rxx of tau is equal to inverse Fourier transform of autocorrelation function. So the Rxx of tau we can write like this: inverse Fourier transform function of where Gxx of f is equal to Sx of f into Sx of f star. So that is the function here we have written. The inverse Fourier transform function f inverse of Sx of into Sx of f star. Writing the above equation in terms of the time domain characteristics of the signal x of t, its autocorrelation function is defined Rxx of tau is equal to, by using limits we are representing, limit t tends to t infinity 1 by t into integral 0 t of x of t into x of t plus tau into dt. So this is the Rxx of tau function. Okay, by the use of two channels, the combined properties of two signals can be obtained. The cross power spectrum of the two signals x of t and y of t can be computed as, here the autocorrelation function for the two signals x and y signals we are representing as G yx of f is equal to Sy of t into Sx of t star. So x term we have taken as a complex conjugated of Sx of t, and here we have written Sy of t, the original form, where Sy of t is the linear spectrum of the y of t, where Sx of t star is representing the complex conjugate of the x of t. So these are the two functions here we have written. So if x of t is representing the input signal, input of the system, and y of t is representing the output of the system. Here x of t, here we have two signals, one is x of t and one is y of t, where x of t is the input of the system and y of t is the output of the system. Then it has a transfer function, that is h of f. It has a transfer function h of f, which contains both amplitude and phase. The transfer function which is consisting of the both amplitude and phase information, and it is computed by using this formula, where h of f is equal to Gyx of f whole bar by Gxs of f whole bar. That is the cross correlation function of x and y, Gyx of f whole bar. In the denominator we have written the autocorrelation function for x of t, Gxs of f whole bar, where the bars indicating the time averaged values. Okay, so finally in this way we are analyzing the transfer function of the system. Okay, so this is about digital Fourier analyzer transfer function. With this one we have completed the digital Fourier analyzer. Let us see once again. The digital Fourier analyzer, it has converting that information into digital form where the signal is waveform sampled for a time t and n samples here we are taken. Here it is using FFT processor, and finally it is displaying the CRT display by using parallel bank filter technique. Here this is x of n into del t. This is the input signal for a wide range of frequency band. For that we have taken the spectral response of Sx of del t, that is we have represented, and this is the complete block diagram of the digital Fourier analyzer. It has three sections: input section, control section and the display section. From the input section the signal is converted into digital signal. The digital signal is going to display the display section, where the control section which controls this information, which information has to be displayed, and the theoretical explanation for the input, control and the display sections. How the transfer function we are obtaining, from the given input signals and auto and cross correlation functions. Okay, thank you. With this we have completed the wave analysis concepts of Unit 2.